One thing we can say for sure about reactions is that reactants diminish and products build up. In this case, we're looking at hydrogen peroxide in the presence of a catalyst, which will make water and oxygen. This can be quite rapid in the presence of a catalyst. What we're going to be looking at here are average rates of reaction. How can we represent the diminishment of hydrogen peroxide and the buildup of water and oxygen over time? An average rate of reaction, by definition, is a delta change. We need to make a few stipulations here. One thing we're going to say is we're going to set this up so that the rate will always be positive, so that whether our reactant or product is increasing or decreasing, we are going to have a positive rate. Reactants, of course, are consumed, so by definition, the change in X will be negative. We can make it positive by simply putting a negative sign in front of our negative change. This looks like the delta change in reactant, the negative of that, over the delta change in time will be a positive rate. Products, on the other hand, are being built up as the reaction goes along. Therefore, the change in X is going to be positive, and we don't have to manipulate anything for it to be positive. Therefore, the rate equals the change in product over change in time. In a given chemical reaction, we have different stoichiometric coefficients. This means that there will be relative rates at which reactants are consumed and products are formed. We therefore need to identify the rate with respect to each reactant and each product, and we're going to see that we need to use the inverse of the stoichiometric coefficient and the appropriate sign to get the proper math for each individual species. In this case, we have a classic combustion reaction. Propane is combusted in oxygen, and we produce CO2 and water. Very exciting. The rate of reaction, following the stipulation of using the stoichiometric coefficients and taking their inverse along with the appropriate signs, means that propane will disappear, as you see here. The stoichiometric coefficient is 1, so it basically drops out. This is going to be equal to the negative 1/5 of the change in the oxygen concentration over time, which in turn is equal to 1/3 of the change in CO2 over time, which is in turn equal to 1/4 of the H2O as over time. This has the very important aspect of making all these rates equal. Another way to think about this is water, in terms of its rate, is forming 4 times faster than propane is being consumed. You can see that for every mole of propane we put in, we get out 4 H2O. Therefore, as noted, the way this works out mathematically is we take the inverse of the 4 to make the rate at which H2O appears equal to the rate at which propane disappears. We can put this to work in a practice problem. We're just going to get some practice here setting this up correctly. We call these rate expressions, average rate expressions, and we're going to look at these two reactions here in order to represent the disappearance of reactants and the appearance of products in each case. In the first one, notice all the stoichiometric coefficients are 1. This actually makes our life pretty easy. We just have to be careful with our signs. So we can set the rate equal to the negative of the reactants and the positive of the products as delta changes of concentration over delta changes in time. The second one is a little bit more involved, and we're going to need to do those reciprocal or those inverse operations on our stoichiometric coefficients. So negative 1/4 here, negative 1/5 here, positive 1/4, and 1/6. Nothing particularly difficult about that. It's just a question of knowing the rule. Now we can use that to evaluate the rate of one chemical in our reaction versus that of another chemical. In this particular problem, we're being told actually, that molecular oxygen is reacting at the rate of 0.024 molarity per second. Let's imagine for a moment that we want to know the rate at which N2O5 is being formed. We can actually do this quite simply because this is very simple math here. We can say, well, it must be forming twice as fast as oxygen because this has a 1 and this has a 2. However, if we use our inverse method, we'll get the same result. We're going to take the negative of the disappearance of O2 over time, and we're going to set that equal to 1/2 the appearance of N2O5 as a function of the change in time. When we do the math, we're simply going to multiply 2 times this rate, which, keep in mind, is actually positive because we always make it positive. And we're going to get 0.048 molarity per second. We could have done this. I wouldn't exactly call this a rigmarole, but we could have seen it right away from the equation. This is the formal way to set things up, and can be quite useful when your stoichiometric coefficients get more complex and it's a little harder to see the mathematical relationship between two different elements in your chemical equation. That's really it for average rates.